I just want to start off by thanking everybody for joining us today and for your participation in the Scripps Technical Forum. My name is Vanessa Scott, and I work in industry relations and innovation here at Scripps Institution of Oceanography. The Scripps Technical Forum is supported by Douglas Alden, who is the Scripps Technical Forum chair. He's also the lead engineer for the Center for Western Weather and Water Extremes, and Douglas normally moderates these sessions, but he is out in the field today, so I am standing in. Also supporting the Scripps Technical Forum is Gwen Nero, who is the Director of Corporate Affiliates, Business Development, Industry Outreach, and Innovation at Scripps Oceanography. We always encourage very interactive discussion during these seminars, so please feel free to enter your questions throughout in the Q&A button down at the bottom center of your screen, and also in the chat, that's fine. And I will be sure to moderate. We will have our presentation from Chad Collett, the CEO of SubC Imaging, and then we will hold the questions till the Q&A session at the end. Also, this session will be recorded and available on the Scripps Technical Forum playlist on the Scripps Oceanography YouTube channel. And you can also find out more information from past presentations and upcoming seminars on our new Scripps Technical Forum website, which will be dropped in the chat. Oh, I see it already in the chat there. So we always welcome your feedback and suggestions on future topics and speakers. So please feel free to reach out to either myself, Gwen, or Douglas to share your ideas and comments on the seminar series. And with that, I am pleased to introduce today's speaker and topic. We're going to be hearing about SubC Imaging's Rayfin Camera-driven Ocean Observatory. We're going to be hearing from the CEO himself, Chad Collett, who is the founder and CEO of SubC Imaging. Chad was born and raised in Newfoundland. He's always had ties to the ocean in both his personal and professional life, with his subsea career beginning with the Canadian Naval Reserves as a port inspection diver. In 2010, he took his unique ability of understanding the professional underwater market and began building SubC Imaging, with the main focus being raising the bar for underwater imaging systems. And with that, I will begin the presentation.
Good afternoon. My name is Chad Collett, founder and CEO of SubC Imaging. It is our honor to share SubC's Ocean Observatory system with you today. This system is purposely made for researchers looking to collect high-quality photos and videos of subsea locations over an extremely long duration. The observatory system is driven by the incredibly powerful and versatile Rayfin technology. In our time together this afternoon, I'll give you a brief company overview. I'll share with you some real-world observatory examples from our friends at University of Washington, Memorial University in Newfoundland, and also University of Victoria, Ocean Networks, Canada. We'll also end today discussing system technology and a live camera demo from our local custom observatory that we've built here at SubC. SubC Imaging develops advanced underwater cameras and video systems. And SubC was created from a passion in oceanographic research and ecological methods. We are not just a manufacturer of high-tech equipment. Our technology is driven by conversations and projects with scientists. Our goal is to generate better quality footage and data for papers to guide ocean tech policy and ocean conservation policy. As a company, one of our passion projects is the Akbar, a deep sea camera trap we developed with Kevin Hardy from Globe Ocean Design in California. And we also work with Matt Mulrennan, who's heading up Project Colossal, which is a not-for-profit with conservation as their primary goal. I'm an advisor on Project Colossal. The prototype Akbar system won the Worldwide Conservation X Prize in 2018. The Akbar is a deep sea camera trap that can be readily deployed from vessels, allowing deep sea exploration at scale. The goal is to provide an inexpensive and easy to deploy tool for conservationists to rapidly and with low cost explore deep sea habitats in order to better understand and protect them. I encourage you to check out colossal.org. With years of experience in our field, we understand the very critical performance required by equipment going out to sea. Oceanographic researchers spend weeks to months planning survey, and it costs a lot to conduct this type of research. Ships are expensive, and that is why we understand that you do not choose your partners lightly. SubC has over 170 clients who operate in every ocean on the planet. So first, what is an ocean observatory? An ocean observatory is a collection of advanced subsea equipment that allows the study of a location for an extremely long time, from months, years, or decades. When subsea locations are observed and measured on a continuous basis, the result is a much higher resolution of data and trends, and you can develop data studies that you couldn't otherwise. Observatories range in depths from coastal regions all the way to abyssal depths, monitoring hydrothermal vents, for example. The observatories pictured here have hundreds of kilometers of fiber optic and power cables, and SubC Imaging has over 20 observatory systems deployed worldwide with our partners. Some real-world examples. Since 2012, the Ocean Observatory Initiative, OOI, in partnership with the University of Washington, has been using SubC Imaging's subsea cameras, LEDs, and lasers to observe the axial seamount. The axial seamount is an underwater volcano located 250 miles off the Oregon coast. This study is part of the Ocean Observatories Initiative, which is funded by the National Science Foundation, NSF, and the OOI is a networked infrastructure of science-driven sensor systems that measure the physical, chemical, geological, and biological variables in the ocean and the seafloor. SubC's cameras are focused on a 14-foot tall, actively hydrothermal venting hot spring deposit called the Mushroom on the axial seamount. Residing on an old lava flow, Mushroom is a metal sulfide chimney populated by communities of tube worms, palm worms, scale worms, limpets, and chemosynthetic microbes. The vent's hot spring fluids can reach temperatures as high as 260 degrees Celsius or 500 degrees Fahrenheit. So that means these creatures can survive temperatures hotter than an oven. SubC's camera systems provide an unprecedented insight into the evolution of the chimney and how these macro and microfaunal communities respond to changes in fluid flow, temperatures, chemistry associated with broad-scale seismic and volcanic activity in the region. Video data from SubC cameras flow from an instrument via a fiber optic cable to a primary node, and from there to the shore station in Pacific City, Oregon. While the feed from the camera continuously streams data, the LEDs are only enabled for a short period of time to take photos and capture video clips. So all of this data from cameras and all kinds of different sensors are fed into a large database, and scientists and researchers can pull from this data to do a lot of different kinds of studies to better understand what is actually happening. The University of Washington's Applied Physics Laboratory used a scripting function to capture a digital still every 30 minutes. They've been doing this using the Rayfin Camera for the past couple of years. In this time-lapse example, you're seeing 20 stills per month over 10 months, from August 2020 to May of this year. It's interesting to see how the environment changes and how the marine growth starts to form on the camera lens as well. We've been building a longer time lapse using stills at video frame rates. So our next goal is to create a 10-month sequence in 10 minutes of video. So each day there are 48 sets of photos, photo every 30 minutes. So we're going to create a 24 hertz full frame rate video from stills, and that'll be 600 seconds total. Some, I think, 10 or 20,000 photos. So stay tuned for that. It's very interesting to see how things are changing over time in very high resolution. And more than interesting, I'm sure there's excellent science that can be done from this. SubC has also worked with Ocean Networks Canada and Marine Institute here in Newfoundland to set up the Holyrood SubC Observatory in February of 2021. The Holyrood Observatory sits in water depths of 85 meters, 4 kilometers offshore, and enables real-time monitoring of the ocean and marine life. The observatory sends real-time data via fiber optic cable on the seafloor. The Holyrood system captures 5 minutes of video every hour to look at subsea critters and animals to see how they're behaving. The observatory lets researchers watch marine life in a natural state, offering insight into how they eat and interact with other organisms, and this paints a clear picture of what's happening in the ocean. in the inshore large bays in the ocean. That's where this is located. And another example here, led by Professor Craig Smith, Professor Lisa Levin from Scripps, and Dr. Fabio De Leo, Ocean Networks Canada. The University of Victoria have been using SubC's Observatory solution for their underwater study in Barkley Canyon since 2014. So in May of 2014, 3 humpback whale rib sections, 1 block of Douglas fir and a block of carbonate were placed at a depth of 890 meters inside the Barkley Canyon. This is a site at ONC's Neptune SubC Camera Observatory. The purpose of this scientific experiment is to monitor the changes triggered by the implantation of various organic and inorganic substrates, as well as monitoring how benthic organisms utilize the sparse food resources available in deep sea settings. It's on a schedule of every 2 hours. The autonomous SubC cameras and LEDs pan to 3 substrates, and while holding in position for 1 minute each, captured 5-minute videos. Setting up a cabled ocean observatory created a permanent presence on the seafloor and allowed long-term observation and some unique science. This also eliminated the need for more costly, time-consuming monitoring via multiple deployments of ROVs or AUVs in order to gather this type of data. With the help of the observatory solution, researchers were able to establish large-scale patterns in biodiversity and ecosystem function in areas where there are whale falls. The SubC camera observatory system is driven by Rayfin technology. The Rayfin camera is built to withstand harsh ocean environments and is a full titanium build, so you don't have to worry about corrosion. The durable and scratch-resistant sapphire lens paired with water-corrected liquid optics means you will always capture the best data for your research. In a cable observatory, you can collect time-lapse 4K or HD video clips and high-resolution digital stills using the scripting function in an open-source API. Many of our observatory systems, deployed by our partners and clients, have been running autonomously for many years now. In a cable observatory environment, the Rayfin is also a multiplexer. The camera directly controls your LEDs, lasers, pan tilts, and other sensors via the plug-and-play auxiliary ports on the back of the camera, so you can simplify your system and reduce potential failure points. The expansion board option turns the camera into an Ethernet mux for 4 devices and a resettable circuit breaker with fault detection. In this example, you can see the following devices are configured: your strobe, there's also options of far red, there's pan tilt, there's lasers as well, and again, they're all resettable through the control interface and through scripting. So the scripting function. For your long-term projects, you can simplify the system by using the scripting feature to capture time-lapse video and stills. Scripting is a simple software language that allows the camera to run autonomously. And I'll show you an example of this in the upcoming demo. So what are the benefits of scripting? Scripting allows the camera to run independently without requiring an additional computer or person as input, so to send commands on a schedule. This reduces system complexity and cost. And so normally underwater systems as well require a data logger. In this case, the camera is also a data logger, so that can further reduce the complexity and the amount of equipment needed. When you need less equipment, usually you have a more reliable system as well. So it also has onboard storage. The Rayfin records and internally stores over 10 hours of 4K video, over 40 hours of HD video, and thousands of digital stills. You can conveniently view and download your footage in real time over Ethernet. And now it is time for a real-time demonstration of the Rayfin that is currently running at our local custom SubC observatory here in Newfoundland. So on the top left here, you can see how much file storage is remaining. This camera has been running a time lapse for a number of weeks. So there are 3.5 hours of 4K left, about 11,000 photos. On the left here, we've got video and file naming conventions, directory settings, so you can add tags. It's got quality from 4K to SD. I should explain how tag works. So you can basically add custom little event tags that will inject the correct year and an hour or whatever other field you select here. We've got another encoder type as well. So we've got H.264 and H.265. H.265 is a higher quality encoding. We have digital still settings that mirror the recording settings. So you have name, directory, tags, as well as JPEG or DNG recording of digital stills. You can have up to 1,000 photos or files in a directory, and before it creates an auto new directory. You can have continuous photos at up to 4 Hertz, and that's adjustable. And you can have JPEG quality of from 1 to 100%. So the water here is fairly green because it's shallow. So the camera has a white balance adjustment set or auto. We can remove some of the green to make it a little more, realistic for human viewing. We can view the photos and video as they're taken. So like I said, this one's been running a time lapse for a long time. So each of these directories has 1,000 files in it. And so we can access all of our files. We can also access the data that's logged each day that the camera's been running. In sync with that, the data logging feature logs data at 1 Hertz. You can have it oriented. You can have the camera oriented a certain way, and that adjusts how the heading, tilt, and roll work. And you can zero it based on your location. There's also NAS storage that you can point it to another device on the network to store to, and when that device, if that device goes down, it will store to internal storage in the camera as a backup. And you've got light and laser settings. Along the top, you've got your heading, tilt, and roll. If you have a depth sensor, it'll show that, and if you have an altimeter or other sensors that we add over time, it will show that as well. We have auto and manual exposure, where we're able to change our exposure time and our shutter speed, or our ISO, or our gain. We are able to adjust your focus from near to far, or full auto with some exposure stops, auto adjustments for exposure. On the bottom here, we have our recording, so we can start recording video at 16:9 format, or we can take a photo. When you take a photo, you get a preview of that photo as a thumbnail, which you can click on to view. So as you take photos and as you're adjusting your settings, your camera settings, you can dial that in very quickly because you can click to see. You can also digitally zoom in. Again, the water quality is not fantastic here. There's a river just north of this, and it's been raining. But you can pan, tilt, and zoom around. There's a flatfish, so we can zoom in on the flatfish and take a photo. On the top right, we have settings from connection settings, so we can connect over serial, static IP, Ethernet. We have Ethernet stream quality settings, so right now it's at 10 megabits per second. We have date and time settings as well, so you can adjust and have a manual date and time, and the camera has an internal clock. And you also can point it at an NTP server, whether that's on board the vessel or online. And then that'll be from microseconds to milliseconds of accuracy. We have different versions and control here. This is diagnostic information. And we have our aux panel control. So you can have different devices connected to the back of your camera, and the camera will plug and play work with those. And this is our scripting feature. So I'll walk through one of the scripts that's currently written here. And this script is running on University of Washington's cameras. So it's setting it to 4K. You can adjust the recording bit rate. So it's setting it at the highest bit rate. H.265 encoding, which is the highest quality. The image format is set to JPEG. Video names are set here. They have a long naming convention that fits their naming convention, and they have stills names that are similar. Setting the 2 aux port devices turns off the aux breaker panel. It disables the strobe, so because they don't want lights or anything running until they need it. Then it clears the registry of previous script, sets the strobe brightness, and when the system date time minute equals 15, or when the system date time minute equals 45. So that's 15 minutes after the hour or 15 minutes to the hour. It executes another script. So that script that gets executed is right here. This script's a little simpler. There's a master script that's executing a couple smaller scripts. So this runs manual exposure, sets the ISO to 200, shutter speed to this, which is in nanoseconds. Enables the strobe, sets the exposure stops back, turns on the different devices, adjusts the pan and tilt, which is also controlled by the camera, to a specific predefined position because they're doing time lapse and they want repeatability. Waits for 2 seconds, takes 3 stills, disables all of that, turns off all the power, and goes back to the master script. Similarly, when system date time at minute equals 30 and system date time.hour is divisible by 2, so every 2 hours on the half hour, it executes the recording script, and the recording script turns on auto exposure, autofocus, turns on the devices again, waits, turns on the lamp at 100%, starts recording for 2 minutes, stops recording, and then turns everything off again. So this happens continuously and has been happening for a long time. I'm not sure if they're currently using the recording, but they definitely are using the digital stills. So I wrote this little script earlier. You can do things like when the depth is greater than 20. So if you have a depth sensor option on your camera, when the depth is greater than 20, you can enable your lamp and laser. You can enable your laser and your lamp, and you can start recording. And this is similar. When the depth is less than 20, you can stop recording, turn off your lamp, turn off your laser. That would just be a little way to automate things so people didn't forget to start recording or what have you. In this example, it just waits for 1 minute and then starts recording and waits for 10 seconds and it stops. So after, that just happens. So that's the Rayfin camera. That's how it works. It's very straightforward. We're trying to make it easy as used as possible. So I'm going to go back to the presentation now. So running our own local ocean observatory here at SubC has been a bit of an adventure and a little bit of a learning curve and very interesting. Lately, the observatory has been getting tipped upside down and rolling sideways. Some days we've been pointing in the opposite direction from the previous day. So for weeks, we didn't know what was happening, and we were blaming high tides and currents. Then our time-lapse scripting captured some interesting photos. We discovered that a beluga whale has been known to visit the area and has taken an interest in our observatory. Apparently, they like the color green. And the rope we've been using to secure the observatory seems to resonate with this particular whale. So in this shot, you can also see the moon in the sky as the whale picks up the observatory and carries it around and drops it. So this time it's facing up, straight up in the air. And it's a pretty cool shot. You'll see this on social media. So our SubC observatory system is purposely made for marine researchers who are looking to collect optical data of offshore underwater locations over an extremely long duration. SubC has a number of other sophisticated systems that can be easily adapted to your requirements. If you're interested in learning more about SubC and our systems, our qualified team can help with your application. Check out our website at subcimaging.com for more, and thank you very much for your time.
Wow, thank you so much for that great presentation, Chad. What incredible images, and the resolution, unreal, and that beluga whale. What a great story. Anywho, Want to open it up for Q&A at this point. Everybody, please feel free to enter your questions either in the chat or in the Q&A button in the bottom center of your screen. I do have some pre-submitted questions that you guys submitted through the registration process I can kick off with as we wait for questions to come in. So let's see, what do we have? Okay, there's a question about what problems does this product provide solutions for, which I know you kind of covered. How do you balance image resolution and data rate?
Okay, yeah, sure. So there's kind of two questions in one there. So often our clients, universities, so I'll answer the problems does the product provide solutions for first. So often our clients, universities, research institutions, and private companies develop their own camera systems when doing complex operations like a time lapse or 3D modeling, kind of applications I just demonstrated. But rather than developing your own system, we've worked with many clients like yourselves, people that are watching here. And kind of already solved many of the problems you might encounter. So what the product does, or what the system does, is basically save time. That's the big problem that it does. It's a big time saver, and you don't need to discover and solve the problems we've already solved with clients like yourselves here in Canada and worldwide. And the other one around balancing image resolution, data rate. So yeah, that's a good question. We don't really have to compromise and do that balance because the camera stores the video and stills in high resolution internally, and you can download it later over low bandwidth or over Ethernet. And so there's not really compromise. I see one there, Vanessa.
Yep.
Biofouling.
Yes.
That's also, yeah, that's the key. That's actually one of the key kind of challenges around like a long-term submersion. So yeah, corrosion, marine growth, those are things you consider. So there's a few methods that are common for dealing with biofouling. One would be, first, you can put a marine coating on equipment. That's less desirable. It's not good for the environment. So we tend to lean towards a couple of other solutions. So UV lights are actually one method. So when you, there's actually some really good papers that are published that I can send some links out to. AML Oceanographic I believe in Canada. They make an interesting product. It's a UV light with a timer, and they have some good papers and things that published that show that first thing that happens with marine growth is you get like a layer form before the marine growth and there's kind of the nutrient layer that forms on things. And then that's what like barnacles and mussels and other things will stick to. And it's kind of a layering process like an onion. So what a UV light will do is kill that first layer before it forms so that you can't get subsequent layers. And that's what like an anti-biofouling paint on a ship will do as well, right? It poisons the initial layer so that you can't form something. So, and the other, we prefer the UV lights over the paint or the coating. There's also wipers. So like just a mechanical wiper, right? So windshield wiper for your camera system. And we've seen those as well. That's a nice, simple solution. Let's see another one there. Maximum operating depth of the camera. So all of our equipment is designed for 6,000 meters. It's all full titanium right out of the box. And you can also do 11,000 meters. We've done that for Marianas Trench, and we know how to. So full ocean depth, and yeah, eventually Europa. Let's aim for Europa next.
Excellent. Thanks, Chad. There's also another question that came in the Q&A. How is the system powered?
So the system, we've got a couple of different power techniques or applications. Normally, most underwater equipment that you'll come across is powered from between, say, 17 to 32 volts DC. So usually 24 is like nominal system power for most underwater equipment. We also have another piece of technology we developed called the PLE, or Power Line Ethernet. That's a type of, it's like a data power mux, where we're able to send power and data over 2 wires over up to 470 meters of cable. So we actually have a client who's using that to make a fairly, like, 100-meter shallow water observatory running on a solar powered buoy floating at sea. That's an interesting one we're working with them on, and that kind of feeds back to one of the first questions of what problems we're solving or whatever. We help you achieve weird, wonderful things. So yeah, just let us know what you want to do.
Excellent. Thanks, Chad. There's a couple questions that came in regarding long-term submersion. So what's the greatest challenge of long-term submersion, and what's the longest duration a subsea camera has run in an observatory?
Yeah, so there's two big challenges around long-term submersion. So one, right, the biofouling, which we just spoke about, and two would be the corrosion. Corrosion would be biofouling has solutions to it. Corrosion can sneak up on you, and also material breakdown. So we had, I believe, the University of Washington dealt with this with their OOI observatory a long time ago. They had a certain type of connector. The rubber, the Buna rubber that was for the connectors that forms the waterproof seal, started to break down over time. And it was actually because they selected ROHS approved, like California law manufactured rubber. But that rubber wasn't tested extremely long durations. So it actually broke down, caused short circuits, equipment damage, and that kind of thing. So the long-term deployment, yeah, there's definite challenges, but we've seen all of it now. And we, like I mentioned in one of the examples there, University of Victoria have been using our camera systems now for about 8 or 9 years in this type of application. They also, and most, if not all of them, yearly they'll cycle out the equipment as well. So you recover your observatory and usually have a backup or an identical one. You put that one down, and then you have another system to test in the laboratory with, and refurbish or clean all the marine growth off of it, and then put it down again.
Excellent. Thanks. There was a question that came in about, you were talking about your hydrothermal vent applications, and they asked about what temperatures can your observatory cameras operate at? So
the cameras are certified or qualified, quality control tested up to 30 degrees Celsius. But the hydrothermal vents are at like 260 degrees Celsius or like 500 Fahrenheit. So, but what happens is all that heat is going up, right? So it's all rising, and you can see like heat waves in some of the images and video. It makes this like kind of Van Gogh effect, which is really interesting. Yeah, we got some really cool pictures of like that, that kind of like polychaete worms and other crabs and things, but like a Van Gogh kind of look because of all heat waves. But the temperature gradient drops really quickly because it's down really deep. So we don't have to worry about that, or at least our partners don't currently worry about it, and haven't so far. We haven't had a camera get cooked yet.
That's good. There's a question that came in about the lasers. What purpose does the lasers have in an observatory?
So lasers are simply for point reference. They give scale and range. And what you would do is, if you have like 2 points that were painted on an object or a subject, a fish, then you can infer the size of the fish, and you can also infer how far away that is.
Excellent. I'm not sure if you just saw the one that just came on asking who designs and builds the cameras.
Oh, great question. So we design everything. So we've designed the full electronic stack. and all of the mechanical structure. Everything is manufactured here in Newfoundland, Canada. We license some electronics components from Sony and Qualcomm. That's like the processor and the sensor. We've got like a quad core 64-bit processor in there. We got a high resolution sensor, GPU. We designed protection circuitry, multiple auxiliary ports, and expansion capability for future kind of development and whatever else we dream up that we want to do. So we're full start to finish development, and we get titanium from Texas. We bring it into Canada. It gets machined in Halifax. It gets assembled here in Newfoundland. We design all the electronics that comes from Germany, Japan, wherever, you know, electronics come from, right? And we put it all together here.
Excellent, thank you. Jules just entered a question asking, have you got any plans for a tethered ROV or even an AUV that would coordinate, maybe recharge, etc.?
We don't design the ROV and AUV systems that the cameras go on, but we do work with partners who have designed exactly what you're talking about there. And I can't talk about it because some of it's on the R&D end, but our cameras integrate fairly seamlessly with those types of systems, given that we have an API. It uses standard interfaces for Ethernet and power and common ranges, right? So yeah, that's something we don't have plans for ourselves, but we're working with people on. So I see price range of systems. So yeah, I can talk about that. So our lights are like a hybrid strobe and lamp. They're a little bit specialized, 6,000 meter titanium, and they start at around 5K or a little less than 5K US. And the cameras range in price depending on if like you're doing like a PLE camera, which is cheaper. So that'd be around 15 to 16K. And the like higher end 4K over fiber optics cameras would be upwards around 20 to 30K.
Excellent. And I guess that dovetails nicely with another question that was submitted previously, asking about your system uses a lot of different tech. Can you buy some of the equipment, or does it all come as a package? Like, what's the purchasing process?
Yeah, that's an awesome question. So we kind of solve problems basically, right? Like we work with you, we can provide a system, or if you are already really technically inclined and just want a thing like just the camera or just a light or just a laser, then we can do that too. We're really flexible. But we'd like to understand what you're trying to do. Like we'll talk to you and figure out, you know, how are you trying to use this? And then we have a client success manager as well who talks with you after, walks through like a tutorial, walks through some training, make sure you're happy, make sure you understand what you're trying to do, or we understand what you're trying to do so we can offer the best help. So it's not just a buy it and see you later. It's more of a, hi, how you doing?
Excellent, thanks. There was a question that was pre-submitted asking about when you're programming the camera to take a photo, is there a way to take a photo if there was something new in the field of view, something like photo radar?
Yeah, so I guess like that would kind of be like maybe like an autofocus. So it's a fully automated camera system. So, and it's fully manual as well. It's got 2 modes. And when in an automatic mode, there's an autofocus algorithm running that can detect changes in subject distance. So if you were running on a battery and there's no human input, if a fish gets in front of the lens, it'll focus on the fish. If there's a background object like a hydrothermal vent or something, it can focus on that after the fish moves out of the scene. Standard kind of autofocus algorithm. I think that covers that question potentially. I don't know what photo radar is, but I'll look it up.
Excellent, thank you, Chad. Does anybody else have any final questions? I don't see any further ones coming in the Q&A. Any other final thoughts that you'd like to share, or places you'd like to refer people to? I know we dropped some links in the chat to some of your websites. I guess if we don't have any other questions come in, I will thank you so much, Chad, for a wonderful presentation. I learned a lot, and I think it was a very engaging conversation. So thank you again. I do want to kind of follow up and just say Please, everyone, feel free to reach out to myself and Douglas Alden and Gwen Nero with any other topics or speakers that you would like to hear from. Oh, we did get a final question come in. Daniel's asking, can you comment on the tow system? Is it ready for delivery now?
It's still in development. If you're familiar with like TRL levels, it's at TRL 7. We've ordered all the parts. We're doing our final. We've done sea trials already. We've collected all the data from that. We're doing our final design review, ordering everything now, and aiming to have production units this summer. So say July, August, that we can sell.
Excellent. Thank you, Chad. Well, I want to thank everyone again, and just wanted to give a reminder, we do have some future Scripps Technical Forum presentations coming up in July. July 14th, we'll be hearing from Nortech, and July 30th, we will be hearing from Blue Robotics. So thank you all so much for your participation today. Thank you again, Chad and team. Appreciate your presentation and your participation, and we look forward to continuing the conversation.
Thanks, Vanessa. Appreciate it. See you, everyone.